Hello everybody, welcome into another lesson. So today is the final lesson of the circles unit. And today we're going to talk about segment lengths in circles. So first case we have a circle where we have two chords. We have chords A, B, and C, D that intersect. And you have AB is broken down into two segments with lengths. I suppose I should probably put a meeting point here, right? We could better list this as, I'll talk about this in a second here. But anyway, you have two chords intersecting inside of a circle. The theorem here states that when two chords intersect inside a circle, the product of the segments of one chord equal the product of the segments of the other chord. So again, chords A, B, and C, D, they both intersect at point E. What you would do is you would take the length of AE, which is A, times the length of BE, since they're part of the same chord, which is B, set that equal to the length of the other chord, CE, with the length of C, times the length of DE with the length of D. That's all that's saying. So you would have AE times BE equals CE times DE, which would give you the lengths of A times B is equal to C times D. And we'll have some exercises to practice all of this here in a minute. There's a couple more theorems I'd like to talk about before we go on to the exercises. Alright. Now let's see the next theorem. You write this out. We'll get the wording right. A long theorem here. All right. So we have a circle here. I'm going to illustrate all this. Alright, so this time here we have a circle where we have two secant lines that are drawn to the circle from an outside point. This theorem states that when two secant segments are drawn to a circle from a point outside the circle, the product of one segment and its external segment equals the product of the other segment and its external segment. So you have secant line AC, which is split into, of course, segment AB and BC, and then you have secant line EC or CE, however you want to say it, split into DE and CD. Well, what this is saying is you would take the length of the whole segment AC times just the outer portion, which would be BC, set that equal to the length of the whole segment CE times its outer portion CD. And then you notice the corresponding lengths. AB has a length of A, BC has a length of B. To get the length of the whole segment, you're going to take A plus B, that would be the length of the whole segment, multiply it by the length of the outer segment, which is B, set that equal to the length of the whole next segment, which would be C plus D, times the length of the outer segment, which is actually C, my bad, not D. That'd be C plus D times C for the outer segment. So, to figure out lengths of two secant lines, you take the length of the whole segment, the whole secant line, times just the outside portion of the secant line that's outside the circle, set that equal to the length of the other whole secant line times the length of the secant line that is just outside the circle. And then I have one more theorem. This changes a little bit here for the next part. Alright, what do we got here? Let's see. Let's draw this illustration here. Alright, let me just set this up real quick and then we'll talk about this theorem. Okay, so now we have a circle where you have a tangent segment and a secant segment originating from the same point outside of the circle. This theorem states to solve for lengths that when a secant and a tangent segment are drawn to a circle from a point outside the circle, the product of the secant segment and its external segment equals the square of the tangent segment. So in this case here, you have the whole segment AC, right? It's kind of like the last theorem. You're going to take the length of the whole segment AC times its outer portion BC, but this time you're going to set it equal to the length of the tangent segment, which would be CD to the second power. And then you see the lengths of the whole length of AC would be A plus B times the length of the outer segment, which would just be B. That'd be equal to the length of the tangent segment, C squared. So the last two theorems were kind of similar. If you had two secant segments, it's the length of each segment. It's the length of one segment times its outer segment. The length of one whole segment times its outer segment equal to the length of the whole other segment times its outer segment. When you have a secant and a tangent together, it's going to be, for the secant line, the length of the whole segment times its outer segment set equal to the length of the tangent line to the second power. And then we actually did talk about lengths of just two tangent lines earlier in the section. A few lessons back, we talked about finding the lengths of two tangent lines that originate from the same point. That theorem states that tangent lines drawn to a circle from a point outside the circle are congruent. So if you had two tangent lines that originated from the same point, they would be congruent. All right, let's do some exercises here. We're going to solve for some variables, of course. So let's draw a nice circle. Actually, yeah, let's do that. What do we got for lengths? Alright, so we're going to solve for x, of course. We clearly here have a circle where you have two chords that intersect inside of the circle. What does that theorem say about finding lengths when you have two chords that intersect inside of a circle? That the product of the lengths of one chord are equal to the product of the lengths of the other chord. So in this case, you would start with 4 times x. So you would take 4 times x, set that equal to 5 times 8. Which of course would end up giving you 4x is equal to 40. Which could only then mean that x equals 10. So yeah, finding the lengths of two chords that intersect the different segments is actually quite easy. You just take the product of each of the segments of one chord, set that equal to the product of each of the segments of the other chord, and then you can solve for x. It's literally that easy. Alright, what's next? Another circle where you have, this time it goes across the northern half, and then you've got this weird thing here. So two more chords intersecting inside of the circle. what do you have here? X and X. You have 9 and 16. Okay, so we want to solve for the length of X again. So these are just two chords intersecting. So this tells you that the lengths of the segments, it's the product of the lengths of each segment of one chord, which would be X times X. We'll start with that. X times X would be equal to the product of the lengths of the segments of the other chord, which would be 9 times 16, which, let's simplify that. X times X is X to the second power. Then what is 16 times 9? That's 144. Now, of course, we have actually a quadratic, but since this is geometry and we're talking about length, we only consider the positive square root. So the positive square root of X squared, of course, is X. The positive square root of 144 is 12. I know I didn't draw these the most evenly, but X would equal 12. That's what you would get. All right, next lesson. Oh, good one. Actually, I'm going to move this over some. There's a reason for that in just a second. Let's draw that nice circle. Okay. What do we have here? Again, not the most even I've ever done, but it'll suffice. Alright, so now we have a circle where you have a tangent line and a secant line that come from the same point of the circle. So what does the theorem say about that? The theorem says in that situation, you take the length of your whole secant segment. If this part of the secant segment is 3 and this part's 4, the length of the whole secant segment is going to be 7. So you would take 7, the length of the whole secant segment, times the length of just your outer segment, which is 3. That'd be 7 times 3. That's going to be equal to the length of your tangent line, which is X to the second power. So you have 7 times 3 equals X squared, which would give you that X squared equals 21. And there are no factors of 21. That's a perfect square. So you would end up just getting that X is equal to the square root of 21. So yes, the answer for X is, in this case, it's going to be equal to the square root of 21. All right, we have another. Let's see. Not the best drawing I ever did, but it'll suffice. Okay, so now we are given a circle in which we have two secant lines that originate from outside the circle at a single point. Whenever we have two secant lines to find the lengths, you're going to take the length of one whole secant segment. For this one, it would be 5 plus 3, which is what? 8. So you would take 8 times the length of just the outer segment of that secant, which would be times 3. Now that's going to be equal to the length of the whole other segment. What's x plus 2x? That's 3x. That'd be times the length of just the outer segment of the other secant line, which would be times 2x. So this is going to simplify into 6x squared is equal to 8 times 3, which is 24. Which means x squared would just equal 4. And the positive square root of both sides would just give you that x has a length of 2. So in this case, x would actually have a length of 2. Next one. I have about 5 more exercises. I think that'll suffice. I think that'll suffice for what we're doing today. Alright. This don't need to be a super long lesson. I know we've had plenty of long lessons lately, and I do apologize for that, but it was important that I teach you. Right? Because if I'm going to teach you something, I think I should do it right. That seems a little backwards to me, but that's what the book has it, so I'm going to go by that. Okay. So clearly we have another circle with 2 secant segments from the same point outside the circle, right? So again, we're going to take the product of one whole segment. If we start with the top one, this x and then the 4, the whole segment would have a length of what? X plus 4. You're going to take that times the length of just your outer segment, which would be what? Times 4. Then you're going to set that equal to the length of the whole other secant segment. You have 3 and 5, that's 8, times the length of just your outer segment here of the secant, which would be times 5. So we have x plus 4 times 4, that quantity is times 4, is equal to 8 times 5. This would turn into 4 times x plus 4 is equal to 40. Which now you can divide both sides by 4. You end up just getting x plus 4 equals 10. It'll save you a distributive step, and then we'll just give you x equals 6. So the answer for this is x equals 6. Should have about 4 more. Oh, this is another good one. Alright. This time we actually have a center of the circle, which will be right here. We have a whole diameter. Okay, so this time we're back to 2 chords intersecting inside of a circle, right? Okay, well, definitely let's start with the first chord here, the x and the x. You're going to take the product of one segment of the chord times the product of the other segment of the chord. Now you're going to set that equal to the the product of one segment of the chord times the product of the other segment of the chord. But running through the origin of the circle here, this is clearly a diameter. This half of the diameter, which would be really this half of the radius, has a length of 3. This half here has a length of 3, right? So that means this radius from O downward is really a length of 6. Because after all, a diameter is a chord, it just runs through the center. That's what makes it the diameter. So 3 plus 3 is 6. That would be the length of one segment of this chord. And then that would have to mean by default, this radius here would have to have a length of 6 also, right? So x times x equals 6 times 6, which would simplify into x squared equals 36, which could then only mean that x would equal 6. So you get that x has a length of 6. All right, should be 3 more and then we're done. Alright, so very clearly here, we once again, this time, have the length of 2 secant segments to the circle, right? Remember, the theorem states that you take the length of one whole segment. Now it gives you the length of this whole segment is x. They were nice and just made it one variable. So you would take x times the length of the outer segment of this secant line, which would be times 5. Now you're going to set that equal to the length of the whole other segment, which would be 6 plus 4, that's 10, times the length of your outer segment of that secant line, which would be times 4. So this is going to simplify into 5x equals 40, which would have to mean that x has a length of 8. So the length of x for this segment is 8, which means this missing piece would have to have a length of 3 if we were asked to solve for that. So x equals 8 in this case. We just got 2 more exercises. Oh yeah, this will be a good one. This is a real good one for a couple reasons. So clearly we're starting off with 2 chords, right? Alright, so we got chords with lengths with fractions. This is really exciting. So when you have 2 chords that intersect inside of a circle, again, you're just going to take the product of each segment of the chord. So the product of the first one would be x times 4.5 would be equal to the product of the segments of the other chord, so that'd be equal to 2 1/4 times 5 1/3. Alright, good, you can all see it. Perfect. Well, I think it's fairly obvious that we should probably go ahead and turn these mixed numbers into improper fractions. So this would end up giving you x times, it'd be 9/2 would be equal to, that'd be equal to 9/4 times 16/3. Well, we notice here in this one you can cancel out a 4. That would become a 4. This will end up turning, of course, the 3 here would cancel out. This would become a 3. So what you really have now is 9/2 x would turn into equal to 12. So it simplifies down now into 9/2 x equals 12, which would turn into 9x equals 24, which would have to mean that x equals 24 over 9, but both of those can reduce further by 3, right? If you reduce both numerator and denominator by 3, you end up getting 8/3. Well, what is 8/3 as an improper fraction? Or as a mixed number, rather? 8/3 is going to be equal to 2 2/3. So, expressing x in the format desired here, which is a mixed number rather, x would have a length of 2 2/3. So that was a good review of fractions. Now I got one more exercise, then we're done. So a rather short lesson today. Alright, let's see this one here. Not the straightest I ever did, but okay, so for the last one here, we have a circle that has a tangent and a secant line that start from a single point outside the circle. Well, let's start with the secant line. If we remember, to find the lengths, you take the length of the whole secant segment, which would be 3x plus x, well, that would give you 4x, times just the length of the outer segment of the secant line, which would be times x. Now you're going to set that equal to the length of the tangent line to the second power. That'd be equal to 10 to the second power. Which, simplifying this, would give you 4x to the second power would equal 100. Which would then simplify into x to the second power equals 25, which we know the positive square root of 25 is just 5. So in this case, you would end up getting that x equals 5. So that's it for finding the length of circular segments, and actually that's it for the circles unit, besides when we go into area problems and we solve for the area of a circle or sectors of a circle. The next unit we're starting actually is going to be about the area of plane figures. We'll talk about like areas of rectangles, squares, trapezoids, parallelograms, and circles. We'll even find areas of shapes like pentagons and other polygons. There's a formula for that. So this is going to really get more into the classic geometry that everyone's used to. It'll be a relatively easy section. So I hope everyone has a great night. Take care.